wanted to give you guys a different perspective maybe than what the video has in D2L. This is a sheet that I use with my on-ground classes, and I'm hoping that it helps with some of the vocabulary and some of the setup in 8.2. So if not, feel free to contact me, and we can always set up a Zoom appointment. But let's go through some ideas and see if that helps. So a hypothesis testing assumes that there is no difference between the data and some claimed or proposed value. We start out with the assumption that the difference is 0, and then we may change our mind if that difference gets too big, and we need to sort of establish cutoffs for what too big or too small means. So the further from 0 our difference gets, the more convinced we are that the differences are real and not just due to some chance. So the test statistic is the difference between your data or your sample and your claimed value. So if that difference is too big, then we say that our data does not match our claim, and we reject our null hypothesis. So the null hypothesis, we always start out assuming our data equals our claim. So it will always have, or always equal some claimed value. So it always has the equal sign in it. So for example, let's take a look at 1. It says identify the null and alternative hypotheses given the following claims, then determine what type of tailed test to use. So we are dealing with 3 different parameters. We are dealing with proportions, means, and standard deviation. Well, this says the claim is 20% of adults smoke. That is a proportion, and so we're going to use the population proportion symbol P and say that the population proportion equals 20%. Well, the alternative would be that it does not equal 20%. So the claim doesn't say less than, greater than, so our alternative would be not equal to. This creates a two-tailed test. So our differences could be too high, or they could be too low. And alpha is the significance level, and it gets shared between 2 tails because we have a two-tailed test. The next claim says the mean pulse rate of adult females is less than 76. So we're talking about the mean, so we'll use the population symbol for the mean. The null is always the equal to, so we're going to start out assuming it's equal to 76, and our alternative is that it's less than 76. So this is a left-tailed test. If those differences get too small, this way, too negative, we're going to reject our claim that the pulse rates equal 76, and we'll go with the alternative, that they're less than 76. The next one says that the standard deviation of pulse rates is greater than 50. So we'll use the symbol standard deviation and set it equal to 50 for our null. For our alternative, we'll use greater than 50. And this is a right-tailed test. Here's our mean of 0. And this is a right-tailed test. Actually, I'm going to use a proper distribution for this. Standard deviations, when you get into 8.5, they have a different distribution. It's chi-squared. So it would be a right-tailed test out here. Looks almost the same, except this is 0 rather than the mean. Okay, so let's get some vocabulary down and work on that. So part of what's helpful when you conduct a hypothesis test steps 2 and 3 of a hypothesis test are basically to find your critical value and then sort of set up how you're going to make a decision. So it really is helpful to have a drawing, and we would really like a visual to see what's going on with a p-value in a critical region. So alpha is the area in the tails, and it is the probability that you're making a type 1 error. So we don't want to, we don't want to make an error. So, but that's our kind of our willingness to make a type 1 error. We're going to set it at 5% for this particular hypothesis test. So that any z-score that we get that's beyond this critical value, we call the critical region, and we would end up rejecting the null hypothesis. So this shaded region up here for those z-scores is called the critical region, and we would reject the null. So we'd like to find this critical value, z alpha. Well, we find that by using inverse normal. So this would assume that we're doing like a z-test for proportions, or one proposition z-test. Since we have 5% to the right, that means we have 95% to the left. If we put that in our calculator, we're going to get 1.645. So that is our critical value. So we would reject any test statistics larger than 1.645. Sorry, we would reject the null hypothesis if we got a test statistic larger than 1.645. That would be up here. So let's suppose that our test statistic is 1.2. Well, that falls right here. The p-value is the area beyond the test statistic into the tails. That is the small red shaded region here. We could find that area by looking at normal CDF from the lower bound, 1.2, out into the tail, positive tail, 1 million. If we did that and rounded to 4 decimal places, we would get 0.1151. We can see that area is larger than, that red shaded area is larger than the test statistic, sorry, larger than the significance level alpha. So that is also another way we can decide whether or not to reject or fail to reject our null hypothesis. Let's take a look at another example. Here, we're looking at a situation where we might have a left-tailed test, and our alpha is 0.10. So this area in the left tail our significance level is 0.10 this time. So this value is our critical value. And we would find that by doing inverse normal. We have 10% to the left. So that would end up being negative 1.28 for a z-score. So this is our critical region, where we will reject the null hypothesis if the test statistic falls there. Suppose the test statistic is negative 2.5. That's this value right here. This is our test statistic. And the p-value is this very, very small red area headed back towards negative infinity. If we used normal CDF from negative 1 million to negative 2.5, we would get a very small p-value compared to the 10% alpha. We would get 0.0062. So in this particular situation, we would reject the null hypothesis because the test statistic falls into the critical region, but also this p-value, because the test statistic is so far out in the tail, the p-value is very, very small compared to this larger area alpha. So another thing you could do is compare the p-value small to alpha. When you have a small p-value, it means that this test statistic was pushed out into a tail, into this critical region out here. So let's write that up a little more formally. There's two ways that we can make a decision. First is we could compare the test statistic, usually a z or a t, to the critical value. And that's that boundary marker for the critical region. If the test statistic falls in the shaded critical region, we are going to reject the null hypothesis. If the test statistic does not fall in the shaded critical region, we will fail to reject. Or we can compare area to area, right? We could compare our p-value area to our significance level alpha area. Those are both probabilities. We could compare the probability of making a type 1 error to the p-value. And then there's a rhyme that's silly, but you could remember it to help remember how to make that decision. So it goes, if the p-value is high compared to alpha, the null will fly, meaning you have to keep it. If the p-value is low compared to alpha, the null must go, meaning reject. So let's look at another example. We'll kind of step our way through a small hypothesis test and write up a conclusion based on our drawing that we had in example 4. It says, what conclusion would you make regarding a consumer claim that cans of tomato sauce labeled 8 ounces actually have a mean volume less than 8 ounces using the 0.10 significance level and a test statistic of negative 2.5? So our null hypothesis is that the mean is equal to 8 ounces. The claim is that the mean volume is less than 8 ounces, and so that is our alternative, less than. So this was our claim. That's step 1, is always to write out your null and alternative. Step 2 would be to find your critical value. Well, this was a left-tailed test with an area of 0.10 in the left tail. We found that that critical value is negative 1.28. Step 3 would be to actually run the hypothesis test like in a calculator or something like that and get the test statistic. Well, we were told that z was negative 2.5. That clearly falls out here. Again, our p-value is very small. I think it was 0.0062 if I recall from earlier. And so that would lead us to, I didn't write it, this is actually step 4 where we find it. But that would lead us to reject the null hypothesis. Right, our critical value fell in this critical region, and our p-value is certainly less than alpha. So we're going to reject HO. Whenever we reject the null, there is sufficient evidence. So we rejected Hugh. That means we are supporting our claim. So there is sufficient evidence to support the claim. And then you just sort of copy and paste what the claim was out of the problem into the line behind. Support the claim that the cans have a mean volume less of 8 ounces. Hopefully that helps define some of the vocabulary a little bit better and break up the two different ways that you should be able to reach the same conclusion. That p-value or looking at the test statistic versus the critical value will never lead you to different conclusions. It's just two ways to look at the same thing. I hope it helps. If you have questions, please don't hesitate to reach out and ask. Thanks.